Hello everyone, I am Fan Yang from ERAU. Today I will talk about relationship between turbulence and atmospheric stabilities reviewed by sodium lidar measurement. This work is supported by NSF grant. The background for this work is atmospheric turbulence plays an essential role in the mixing and diffusion of momentum, mass, and energy in MLT. Turbulence can be generated through mechanisms such as convective and dynamic instabilities. Gravity waves produce large wind shear or large lapse rate, which can lead to instabilities. Here is the motivation. Sodium lidar has been proved to be able to measure the effects of turbulence on the atmosphere in Guo et al. 2017. This work has two goals. First, it will expand data used from 7 nights to 160 nights in every calendar month, enabled by a large increase in allo lidar operation from 3 to 4 campaigns per year to monthly operation in 2019. And thanks to the increment of the observation hour, we can study the different effects of turbulence in unstable and stable regions of the atmosphere. The data I use is sodium lidar data from Andes Lidar Observatory, located at Cerro Patron, Chile. Here, allo sodium lidar measures line of sight wind at a temperature in 80 to 105 kilometer range at high resolutions. It's about 1 minute and 500 meter. The lidar has two operation modes. The first mode is the zenith only mode. In this mode, the laser measures temperature and vertical wind. The second mode is 3D mode. In this mode, the laser was set toward the zenith and 20 degrees off the zenith toward east and south in sequence, like this. 1 minute in each direction, measure temperature and 3D wind. The raw photo counts were recorded at 6 second and 25 meter resolutions. In this study, 160 nights totally, 43 nights zenith only, 117 nights with 3D wind measurement were included. The orange color represents the night of 3D measurement in each calendar month. The gray color represents the night of zenith-only measurement in each calendar month. The data process shows how we get the turbulence perturbation. Turbulence scales are small, up to a few tens of seconds and a few tens of meters. LiDAR does not have sufficient SNR to directly measure temperature and wind at these scales. So we need to extract the temperature perturbation and wind perturbation from photo count fluctuations based on linearized T, W, and photo count relationships. This approach is called signal perturbation method. Detailed process are derived in Gardner and Liu 2014, Guo et al. 2016. In practice, T, W are linearized with respect to ratios RT, RW, used in 3-frequency method. The flow chart shows the difference between traditional method and the signal perturbation method. Traditional method derive the perturbation of temperature and wind directly from T, W themselves. In SPM, we first remove the background ratio at gravity wave scale, then we get the turbulence scale fluctuations of two ratios. And then we use the linearize the TW and the photo count relationships. Turbulence scale fluctuations can be derived. There are two types of turbulence fluctuations. For zenith-only nights, turbulence fluctuations were extracted by removing fluctuations with scale larger than 5 minutes and 2 kilometers. Only convectively unstable regions can be studied because of no horizontal wind measurements. For nights with 3D wind, turbulence fluctuations were limited at scales less than 1 minute and 2 kilometers. Both convectively and dynamically unstable regions were studied. To study the turbulence influence on unstable atmosphere, we need to identify the unstable regions. Data were separated into stable and unstable regions based on n-square and Richardson number. The left plot is the distribution of n-square with respect to altitude and the UT time. The right plot is the distribution for Richard's number with respect to altitude and UT time. For n squared less than 0, it's the convectively unstable region. It's the blue area in the left plot. For Richardson number between 0 and 0.25, it's the dynamically unstable region. It's the red area in the right plot. Turbulence heat flux was calculated separately using the data in each region. We study the effect of turbulence by studying the turbulence parameters. The first parameter is heat flux, calculated as the covariance of W prime and T prime. Potential temperature for a stable atmosphere increases with altitude. A mixing process brings large potential temperature downward and brings small potential temperature upward. So the heat were moved downward. So generally, heat flux for very long period of data is downward. For a localized turbulence, the potential temperature profile can be locally reversed, so the mixing may transport the heat upward. We first show the heat flux derived from zenith-only data. The heat flux for stable region are very close to the heat flux derived from total data, so we didn't show it. The left plot is the heat flux using data on zenith night. The blue line here is the heat flux calculated from convectively unstable region, and it's marked as CI. The black line is the heat flux calculated from the total data, it's marked as all. The right plot is the total times of data used to calculate the turbulence heat flux. The time for zenith-only data observation is about 200 hours, and the unstable region for all altitude is less than 10 hours. Turbulence heat flux in convectively unstable regions is much larger than the overall average heat flux. Here shows the heat flux derived from 3D data. The left plot is the turbulence heat flux using data on 3D wind nights. The red line here is calculated from dynamically unstable region, which is marked as DI. The right plot shows the total times of data used to calculate the turbulence heat flux. From this plot, we can see the turbulence heat flux in dynamically unstable region is smaller than in the convectively unstable region. And I want to point out again, for 3D data, only turbulence less than 1 minute were included. And then we check the total turbulence heat transport. It's calculated by this formula, the heat flux multiplied the time. The left plot is the total heat transported for zenith-only night. The right plot is the total heat transport for 3D wind nights. The generally turbulence transport heat downward. The total heat transport in unstable regions is much smaller than the total heat transport on all nights because of the short duration of unstable atmosphere. These two plots are close look for total heat transport for unstable regions in previous slides. Then we check the turbulence heating rate. So we only show the heating rate for zenith-only night because the heating rate for dynamically unstable region is small. Turbulence heating rate in convectively unstable region creates cooling above 29 km and below 87 km, and heating in between on the order of 2 to 5 K per day. The overall turbulence has a cooling effect of less than 1 K per day. We also studied the turbulence thermal diffusion coefficient KZZ. The magnitude of the diffusion coefficient is proportional to the magnitude of heat flux. The black line is the diffusion coefficient of total data for zenith-only nights. The blue line is the coefficient for convectively unstable region for zenith-only nights. The red line is the coefficient for dynamically unstable region for 3D wind nights. Turbulence thermal diffusion coefficient in convectively unstable region is much larger than that of overall coefficient. The diffusion coefficient in dynamically unstable region is smaller than that in convectively unstable region. But the coefficient in dynamically unstable region is derived from 3D data. Only turbulence less than 1 minute were included. I will summarize the conclusions. High-performance sodium lidar can be used to study relationship between turbulence and atmospheric stabilities. Turbulence heat flux in convectively unstable region is much larger than the overall averaged heat flux. Turbulence heat flux in dynamically unstable region is also large, but smaller than in convectively unstable region. It could be due to the data limitation. Overall heat transport is dominated by turbulence in the stable atmosphere because of the short duration of unstable conditions. On average, turbulence has a small cooling effect in mesopause of less than 1 Kelvin per day. Turbulence heat flux in convectively unstable region results in cooling above 92 km and below 87 km, and heating in between on the order of 2 to 5 Kelvin per day. Turbulence heat flux in dynamically unstable region is smaller, likely due to data limitation.